Hello kidlets, this is your first video for stars. Each of these subsections will likely be broken up into smaller subsections. And this is a pretty large unit because we are covering everything from the interstellar medium to the formation of stars to our nearest stellar neighbor, to the death of stars and how that affects the universe and us. So we are covering essentially about 6 units in one. So the first couple slides here are going to talk about the interstellar medium, cosmic dust, which we've largely looked at in our cosmic dust lab. I'm not going to spend a ton of time going over this because we are just going to jump right into our star. But the big takeaway is that the ISM, or the interstellar medium, as it is otherwise called right here, is something that we can detect. It alters light from stars. As we've seen in infrared, you have a scattering of blue, so we would see more reddening, so we can see stuff that is cooler. And the interstellar medium is essentially the breeding ground for stars. So we can see evidence of stars that are being born, evidence of stars, gas and dust left behind from stars that die. So the ISM is really where we find all of that evidence of stellar nurseries, where stars are being born, and then the clouds that birth those stellar nurseries. So here we can see some reflection nebulae. So more gas and dust means more star formation. More dust reflects more starlight. So here's a dark nebulae, so we can see that this has a lot more likely infrared in these regions that are scattering all of the blue. They block light. And I know this title is tough to see. It says, what are the characteristics of interstellar dust grains? So as we've seen, that needs to be a certain size in order to clump, in order to give us star-forming material. And here is just a survey of a Bok globule, which is a type of star cluster. So now taking a look at the sun. If we were to compare this guy right here, which is not a flare, it is actually a prominence. A flare is something that ejects out into space. We can see how much larger comparatively just that solar eruption is than our little teeny tiny Earth here. And that's not to say that we have a hugely large sun or a very bright sun. It's just a whole lot bigger than everything else we have in our solar system. And it's actually a dwarf star. But the sun is large enough to be able to contain everything within our solar system, all of the space rock, every one of the planets, and still have tons of extra room. So it is the center of mass for our rotational system. So we can see, if we were to look at some comparative characteristics between the sun and the Earth, if we just take a look at the solar temperature compared to that of the Earth, it is significantly warmer. However, remember, our sun is not a hugely hot star. It is a pretty mediocre star. There are stars that are 100 times hotter than our sun. And when we talk about the temperature, we're talking about the surface temperature. The internal, the core temperature, is 1,000,000 degrees. It has to be, or it couldn't complete the solar processes of fusion. We can see the mass exponentially larger, diameter much, much larger. But then if we take a look at that density, it should stand out that the Earth has a much higher density than does that of the sun. And that's because the Earth is a small rocky body, whereas the sun is a large gaseous body. So the Earth is actually a much higher density. That might be a question I might ask you, of which of these, being able to identify which characteristic is true. We can see, if we take a look at the energy, so 10 to the exponent of 26 watts, that is a lot of joules per second. So that would be somewhere around the order of 26 zeros joules per second. Watts and joules would be units of energy. If we compare that to the energy released by Hiroshima, the most famous nuclear bomb, Hiroshima released about 12 kilotons of TNT, which is equivalent to about 6 times 10 to the exponent of 13. Which is a lot smaller than that. And if we compare that to the Tsar bomb, which is the largest bomb ever, which is 50 megatons of TNT, that only has an exponent of 17. So we can see that the sun has a whole lot more energy. There's 109 Earth diameters and over 1,000,000 Earth volumes. So one of the questions that I would expect you to know would be, if the sun is a low mass star, how does that star compare and contrast with our Earth? So you would need to be able to comparatively state some of those characteristics. So the next thing we're going to look at is the internal structure of the sun. And we can think about the sun as having 6 distinctive layers. We can see the photosphere, which is what we call the surface. When we talk about the temperature of the sun, we're talking about the temperature of the photosphere. Sorry, that went off the screen there. So the photosphere is what we call the surface. That is the color yellow/orange that we see in our sky. We are seeing the photosphere. Just above the photosphere, we have the corona. So right now we're looking at the layers of the solar atmosphere. So the layers of the sun's atmosphere can be broken down into photosphere, which is the surface, the chromosphere, which is just above that. This radiates in UV only, and then the corona, which is out here, which is visible only in X-ray and gamma ray. We can only see that layer during a solar eclipse. Then beneath the photosphere, the apparent surface of the sun, we have the convective zone, and this is where we have that convective flow of heat rising and cold sinking, transferring energy from the radiative zone. So below the radiative zone is where we have this energy transport from the core all the way out to convective, and then we can see the evidence of the convective zone on the surface as we have surface features. And then in the core is where the energy production of the sun is. So we have some different types of energy transfer going on within the sun. If you remember your types of energy transfer, we have conduction by heat or by a direct contact. We have convection, which is the rising and falling of a substance. And we have radiation, which is traveling through open space. So energy is always transferred from hot to cold. That takes the least amount of energy. It takes no energy input. And through a star, we have that methods only through radiation and convection. No conduction, because we would definitely not be touching the sun. And although the layers touch each other, we're talking about movement of photons. So radiation, it was in terms of photons traveling through the sun. And this happens through that radiative zone, if you remember that layer that is just beneath the photosphere. And it can take a photon hundreds of millions of years to travel from the core through the radiative zone out to the photosphere. And the smaller the star, the smaller that radiative zone is. Then we have convection in the convective zone, which is evident in all stars, and the smaller stars are nearly all convective. They do not have a radiative zone at all. Our star does, but when we get smaller than our star, that zone shrinks, and we have a convective zone that is touching the core. And this is where we see the effects of that radiative zone. So we see that energy and that heat, the high energy photons reaching the convective zone. We see them rising and sinking, and we see the evidence of that on the surface of the sun. So in the interior is where we have the core, which is where our production center of the sun is. So this is where we have fusion that happens. And the core of a star has to be 1,000,000 degrees in order to have fusion at all. Next, we have that radiative zone where we have that energy transfer of photons leaving the core, traveling outwards towards the surface, passing through the radiative zone. And then we have that convective zone. We can think about that as being like boiling water in your home. This is an area of boiling fluids that are rising and sinking as a result of those high energy photons traveling from the core through the radiative zone to the convective zone. Once they leave the convective zone, then we can see the photosphere. And the photosphere is what we call the surface of the sun. So this is where we have photons that leave the star, and we call this the surface because this is the only portion of the sun that's black body peak curve is in the visual portion of the spectra, and it happens to be in the yellow portion of the spectra. So we cannot see the chromosphere, we cannot see the corona, we cannot see the convective zone in the visual portion of the spectra. We can see the photosphere, so that is why we call it the surface. And its peak, again, is in yellow. That is why we see it as yellow. So this is where we see the evidence of things like sunspots and flares, which are the direct outcome of that convective zone, where you have that heat rising, cold sinking. And that gives us something called granulation, which is essentially bubbles. So you have that convection, just like if you look down on boiling water and you can see bubbles on the surface, granulation is bubbles on the surface of the sun. And the surface of the sun is actually the coolest layer. It's somewhere around 5,000 degrees Kelvin, whereas the corona is 1,000,000 degrees and the core is 15,000,000 degrees. So here we can see another image of that convective zone as it reaches the photosphere. So here would be subsurface, and we see that heat rising, cold sinking. We see this constant convective flow, but then on the surface we would see these granules, this granulation, and these can be very, very large, and they can last for minutes, seconds, or days. And we believe that the granulation is a direct cause of the flares that we see, that it's all related, that it all starts subsolar surface and gets expressed in the photosphere. So here is another image of that granulation. I know this looks very small. It looks like grains of sand. These are all about the size of Texas or the US. So, and these are constantly moving. The sun is not static. So this would be a constant movement and bursting of bubbles. And I have a little video here we'll watch in class. Moving towards the atmosphere of the sun, we have these two major layers. They both start with C. We have the chromosphere and we have the corona. And what's distinct about these is they cannot be seen in the visible at all. So although these are hotter, although these extend further, we would not consider these the surface of the sun. These are extending outwards from that surface, from right here. And these are not visible in the visible portion. We can't see these. We can actually only see both of these during a solar eclipse. So the chromosphere, we can have the expression of that convection in things called spicules, which can radiate out. They kind of look like hairs. In the chromosphere, we have an increasing temperature all the way outwards towards the corona, which is the hottest layer of the sun's atmosphere. The core is the hottest layer of the interior. So the chromosphere is visible only in UV because we have that black body curve, which is now shifted outwards of the visible and towards the higher energy UV portion of the spectra. In the corona is where we get the phenomena of solar wind, which is something that is not entirely understood. We have multiple solar probes right now looking at that because the solar wind is what generates our auroras. The solar wind can be very dangerous for us. And we think that the solar wind is tied directly to solar flares, so solar activity. So that's what we really want to be monitoring. And that's where we get that stream of high energy particles that can be damaging to electronic devices and people on Earth. So here is where we have very, very small ionized particles and plasma, and this is visible only in the highest energy portion of the spectra in gamma, X-ray, and UV. So here we can see those outer layers of the sun, visible only in eclipses. So here we have two different images of eclipses. We have an eclipse here, we have an eclipse here. You can see the polarity of the sun and how we have these polar regions of magnetism. And that's really what you're viewing here is the effect of magnetism. The sun is like a giant, giant magnet. And as we'll see in the next section, looking at sunspots, those are all a consequence of the intense magnetism of the sun. So we can only see these layers if we block out the sun. So all of our solar probes, which are looking at the sun, mimic a eclipse. So we call those coronagraphs. So this is taken from the SOHO Observatory, which is an orbiting observatory looking specifically at solar activity and activity within the corona. And it mimics an eclipse by blocking it out. And we can see here, this is called a CME, a coronal mass ejection, visible only when we completely block out the sun. So, and then if we don't block out the sun, we can't see that at all. So eclipses give us important information about our star. And we can see on the edges, we can see some different solar activity too. And then when we block it out, we can see these high energy events, which can sweep across Earth and be really damaging. So here we can see looking at some comparative temperatures. Remember, the photosphere is the apparent surface. So here we're moving away. We're increasing height away from the surface of the sun, and we can see what begins to happen to our temperature. We can actually see the temperature of the sun decreases towards the chromosphere. Then we have a steady, steady incline here. We have a plateau in the corona, and we have this area where it gets incredibly hot. And that's something that's not entirely understood of why the corona is as hot as it is when it's so far away from the sun. What is it that is ionizing those particles, making things so high energy that you have such a high rate of collision that is causing it the temperatures to be elevated that high? Between 5,000 up to 1,000,000 is an incredible increase in temperature, and that's something that scientists hope to understand with a lot of the orbiting observatories currently. So that is your first notes video. I will see you in class. Have a wonderful day.